0. Where does A exist now? A कहाँ पे है? Word 3 में A stored है. This block is not only bring into the last level cache, but it's also bring into the this L1 cache. Why it is brought into L1 cache? Because T1 is accessing this data. So this read A is from T1. Where T1 is executed? Task T1. Microprocessor. Task T1 is now executed on microprocessor and it wants to read A. Initially this is a miss. There is a miss in all caches. What will happen? You bring the block from where? Main memory. And where you do place it? Last level cache, L1 cache and L2 cache. So now this MBJ exists in L1 cache, MBJ exists in L2 cache and MBJ exists in last level. Which property is this? Inclusion property. Inclusion property says if a block exists here, it should also exist here and it also exists here. Okay. Now after some time you say read A. It's a hit or a miss? Hit. Read it or write it? Read it. Let's assume that the initial value of the block A is 35. So what will be the value of this word 3? 35. What will be the value of block here? 35. What will be its value here? What will be its value here? 35. Now, after some time, you want to perform a write operation on this word. What will happen? It will be read it or write it?
Right.
Huh?
Right.
It will be a write hit. When it's a write hit, so what will be the new value in L1 cache? The new value will be 5. And which bit will be set in the cache?
Dirty bit.
Dirty bit. Dirty bit will be 1 or 0? 1. Okay, now it executed. Now let's assume another scenario. When task T1 is finished, task T1 is finished, and task T3 is then mapped to this microprocessor. Task T3 is mapped to microprocessor. Okay. If this does this block exist in this L1 of this cache or not?
Yes.
No. It only exists in the L1 of T1, not in the L1 of T3. This microprocessor 2. When this application is running here, it bring the block from the LLC and put it into L1 and L2 cache. But when this task T3 is mapped to this microprocessor, so initially the cache is empty or full? Empty. Or it has some other blocks, maybe some other task is mapped. And it has not referenced this main memory block 5. But this microprocessor access this block A, now in task T3. We are reading from A or writing to A? Reading. So what value should we read? 5 or 35? 5, not 35. But the block that exists in the last level cache, what's the value in the last level cache? Word 3. 35. So when there is a miss in this microprocessor 2 and it wants to read some data, so from here it will load LLC, L3, actually LLC last level cache, we call it last level cache or L3. When it will read from L3, will it read the old value or a new value? Old value. will the program be consistent or inconsistent? Inconsistent. It means that the cache are now inconsistent. This problem is called as cache coherency problem. The cache coherency problem exists. देखिए ये तो मैंने आपको एक एग्जांपल से समझाया, पूरी कंप्लीट मैंने आपको एक्सप्लेन किया, प्रोग्राम से सारी चीज़ें एक्सप्लेन की है. लेकिन if you look at the cache coherency problem, the cache coherency problem arises. The cache coherency problem arises when a block is modified into the private cache of one microprocessor. Okay, and the other microprocessor does not have the updated copy of that block. Does not have an updated copy of that block. So this problem is called as cache coherency problem. The cache coherency problem. Okay, how we can solve this cache coherency problem? It means that the block that exists here is not consistent with the block that exists here. So it means that this microprocessor 2 should have now an updated copy. How we can solve this problem?
By enforcing inclusion property.
ना inclusion property का आपने enforce कर दिया, तो कोई नहीं है ना. ये तो L1 and L2 cache, आपने inclusion force भी कर दिया.
सर इसका ये हल हो सकता है कि हम उसको वेबसाइट तरीके से डॉक्यूमेंट को दूसरी जो हमारी कॉपी दूसरी डॉक्यूमेंट को चेक करें डॉक्यूमेंट
तो किस कॉपी करोगे? There are two possibilities. There are two possibilities. The possibility is when this microprocessor wants to write some data, so it needs to have some bits, additional bits. We need some additional bits in the block. So we can call it P or S. P or S. So P or S is a bit that is either 0 or 1. When it is 1, 0 it means it is a private copy, and it is 1, it is a shared copy. Okay? So if it is a private copy, should we modify it? No. But if it is shared copy, then you should look for the other cache. So in a multiprocessor based system, there is also another addition annotation that the blocks data exists in the memory. So actually for each block in memory, there is one parameter that is called as S or P. S or P. Some data that is exclusive to one application. It is not shared between other applications. So in that case, you don't need to check for cache coherence. But when it's a shared copy, then you need to check for coherence. So now, how does it happen? Now, if you look at the memory map, how does the operating system divide into? It's very important. It's very important. Here, now let's assume we have a main memory. We have divided this main memory address space into multiple sub address spaces. Okay. So now we say processor 1, this is processor 2, this is processor 3, and this one is processor 4. So actually this address range belongs to processor 1. This address range belongs to processor 2. This belongs to processor 3. This belongs to processor 4. And there is also some shared space. So all the main memory blocks that belong to P1, P2, P3 and P4, they are private or they are shared? They are private. Private for processor 1, private for processor 2, private for processor 3, private for processor 4. And this data is shared upon all cores. आप लोगों ने कभी ऑपरेटिंग सिस्टम पढ़ा है? म्यूटेक्स जब कोई शेयर्ड वेरिएबल, इफ यू वांट टू एक्सेस अ शेयर्ड वेरिएबल, आप पहले क्या करते हैं? लॉक लगाते हैं. लॉक इस वजह से लगाते हैं कि बिकॉज इफ दैट variable is shared between multiple programs, if that variable is shared between, or that data is shared between multiple programs, and one program has written it, but other program has not read the updated data. So actually, when an operating system, when there is a shared variable, so there is also, and this information is given by the operating system to the cache, that whether it's a private copy or it's a shared copy. ओके, आपने सीमाफोर्स किए होंगे या नहीं किए? सीमाफोर्स ऑपरेटिंग सिस्टम किसने पढ़ा है? हाँ, तो उसमें क्या होता है कि जो शेयर्ड वेरिएबल्स होते हैं, तो शेयर्ड वेरिएबल में होता है इस तरह से, और एक्चुअली दिस इंफॉर्मेशन इज गिवन बाय द ऑपरेटिंग सिस्टम टू द कैश आर्किटेक्चर, दैट ओके नाउ दिस इज अ शेयर्ड कॉपी ऑफ द ब्लॉक, और दिस इज द व्हेन इट्स अ शेयर्ड कॉपी ऑफ द ब्लॉक. सो एक्चुअली व्हेन दिस इज इन L1 and you want to access a private copy, should you look at this copy into other cache when it's a private copy? No, but when it's a shared copy, then you should look. You can solve this problem with assigning additional bits with each main memory block in the cache, that whether it's a private copy or it's a shared copy. Now if it's a shared copy, now there is an additional complexity. If it is a shared copy, so if there are 16 cores, और हर एक की अपनी अपनी प्राइवेट कैश है, और हर शेयर्ड कॉपी के लिए फिर आपको क्या कितनी लुकअप्स करनी पड़ेंगी? 16 लुकअप्स. इज इट स्केलेबल और नॉट स्केलेबल? अब नहीं समझे? Now we are studying one thing. When it's private, you should not look into any other private caches, not a problem. But when it's a shared copy, so now let's assume we have 16 core architecture. Now we have 16 core architecture. Core 0, core 1 and up to core 15. And this core has some data that is shared in cache. And you want to read this data. It's not necessary कि वो data updated होगा. लेकिन to maintain consistency आपने क्या करना होगा? तमाम कोर्स के प्राइवेट कैशेस को लुकअप करना होगा. क्यों लुकअप करना होगा? क्योंकि उसने कोई मॉडिफाई तो नहीं किया, उसके पास अपडेटेड कॉपी तो है या नहीं है. ओके, सो हाउ यू कैन सॉल्व दिस प्रॉब्लम? जरा सोचिए कैसे सॉल्व.
Dirty bits.
डर्टी, देखिए आपको क्या पता है उसकी डर्टी बिट क्या है? डेफिनेटली यू नीड टू लुक द डर्टी बिट ऑफ कोर 15. There is a coherence directory. We call it as coherence directory, and that directory is shared among all cores, and they look into the coherence directory. Before accessing the data, they go, what information do we need in this coherence directory for any block? We can also call it in a shared. So in a shared data, so we can assign one bit 1, 2, 3, 4 for each core. Core 0, core 1, core 2 up to core 15. So it means if this pattern is like this 1, 0, 0, 0, 0, 0, 1, what does it mean? This data is now shared between core 0 and core 15. So if the coherence directory says, okay, now it is a 4 core system, C0, C1, C2 and C3. So if this value is 0, 0, 1, 1, what does it imply? A copy of this data exists in which core? Core 2 and core 3. And if there is a, let's see, if this core 3 wants to write this data, if it wants to write this data, what should it do? It should update all of the other copies. देखिए वन मैकेनिज्म क्या हो सकता है? वन मैकेनिज्म ये हो सकता है कि नाउ इट्स अ शेयर्ड कॉपी. व्हेन देयर इज अ शेयर्ड कॉपी एंड वन कोर वांट्स टू अपडेट दिस कॉपी, one core wants to update this copy, it will broadcast all of the other cores. एक तो ये है. एक्चुअली इसमें राइट ट्रैफिक ज़्यादा होगा या कम होगा? राइट ट्रैफिक ज़्यादा होगा. अच्छा, अदर थिंग, अगर हम कोहेरेंस डायरेक्टली करें और फिर हम वहां पे मॉडिफाई करें कि कौन कौन से कोर्स इसके पास कॉपी है, तो फिर क्या होगा? कम होगा. ओके, नाउ I will explain this with another example. Now let's assume that there are 4 cores: core 0, core 1, core 2, and core 3. And now we have a coherence directory. The coherence directory. Actually, and now we have some main memory block J. There is a miss. It does not exist in the coherence directory. And core 0 requested this. Core 0 says MBJ. Word 5 of MBJ. No other core has access. So it's a private copy or shared copy? Private. So what will be the coherence bits? This MBJ will be brought in this cache, L1 cache, and the coherence directory will become like this: 1 0 0 1 0 0 0. Okay, now the bits are 1 0 0 0. It means that which core has requested it? Core 0 has requested. Now at other point, C2 also wants the same copy of the data. C2 say I want MBJ. What will happen? What will now be new value? 1 0 1 0. What does it imply? Now this MBJ also exists in L1 of this and L1 of this cache. Now this block exists in 2 different cache. Okay. Now next time you want core 0 wants to write MBJ. What should it do? Core 0 wants to write this data, update this data. What should it do? देखिए पहले तो रीड हुआ ना, रीड हुआ, रीड कॉपी आपने यहाँ रीड का L1 रीड है, L2 both are the same data. Core 0 wants to write MBJ. What should we do now? हाँ? अपनी कॉपी एडिट करेगा, but it should inform whom? Core 2. So if core 0 wants to write MBJ, it will look into the sharing vector. And sharing vector is stored where? Where it is stored?
Directory.
Coherence directory. Coherence directory is shared among all private caches. It will inform the coherence directory that now this copy, this block, this. Okay, now what does it imply? This coherence directory says that this MBJ now exists where? In core 0 and core 2. Now if core 0 wants to write MBJ, it should not only update this copy, but it should also update this copy. And both will be updated. The data will be consistent or inconsistent? Consistent. So this is called as cache coherence. And there are, okay, now if we don't have, if instead of these multiple bits, if we have one bit, private and shared, what's the disadvantage? One bit.
We don't know where it is.
We don't know whether this copy exists where. So when it is shared and when one core updates it, then it should update it in all other cache, independent of that whether that data exists in that cache or not. So this is called as cache coherence. Okay, now this is one level of cache coherence. That how we can maintain it. Okay. Now this is one way. This is one way in which we can maintain cache coherency, but this is very expensive. This is very expensive. Maintaining this coherence is basically you have to look. You have then a coherence directory, and the coherence directory you have a sharing vector, and sharing vector will tell which of the cores has a copy of data in which caches. And when one of the core wants to write that man memory block, it will be updated in all of the relevant cores. And if you have one bit for each core, so it increases the metadata. याद है कैश में कौन कौन से डेटा आप स्टोर करते हैं? टैग बिट्स, then dirty bits, and instead of dirty bits you also need additional bits. कौन से bits you need? Coherence bits. Coherence bits. If you have one bit P and S, what is the advantage? Less storage requirement. Less storage required because you only need one bit, whether it's private or shared. But what's the disadvantage? When it is shared and we want to update the data, then you need to inform all the cores. Okay, now if we increase instead of private and shared, if we have a sharing vector, what is the advantage?
सिर्फ उसको करेंगे जहाँ पे
You only need to inform the core which has a copy of the data. You don't need to inform all of the core. You don't need to send a broadcast message. Instead of a broadcast message, you need a dedicated message to the cores which has a copy of that data. But what's the disadvantage?
वेक्टर का साइज ज़्यादा है
Vector का size ज़्यादा होगा तो you need more metadata in the tag array. You need more metadata in the tag array. What are the metadata in the tag array? What are the examples of metadata in the tag array? Which bits are there? Dirty bit, valid bit, tag bits, and then coherence bits. Then also coherence bits. It also exists. Okay. Now there is another mechanism. There is another mechanism to solve this coherence problem. One is called as the write back policy. And now we have a write through policy. So coherence can be maintained through write through policy. And write through policy says for the sake of simplicity we assume only two cores, core 0 and core 1. Now we have this shared cache. Now listen, if you have some blocks from main memory, maybe this block is MBJ, and if it does not exist in MBJ, you put it in here, and then if this core request is, you put MBJ here. The problem exists when this core modifies this data. So now let's assume the value of this MBJ is initially 5. And after that, sometime this core update this and this is 9. So which one has the updated data? Core 0 has the updated data. This one is updated data or unupdated data? Unupdated data. This is the old data. We call it stale data, incorrect data. Okay. Now if core 1 wants to read this data, will it get the right data or false data?
false data
False data. So actually, we can solve this problem using write through policy. In a write through policy, let's say this MBJ value is 5, you brought it in here, you brought it to 5, no problem, does not exist. But if this core wants to read this data, it will read this data, no problem. But if this core wants to write this data 9, it is not only written here, but it is also written here. So this code does not have any dirty data. Whenever the data is updated in the core or the lower level cache, it is always updated in the upper level cache. So when this code wants to read this data, the probability it will read the data, it will always get the correct data. Correct data. So what is the advantage of this write through policy?
हर वक्त उसे करेक्ट डेटा मिलेगा
Correct. What is the disadvantage?
अगर ज़्यादा राइटिंग करेगा ये तो
So it is more write traffic from the core to the shared cache. Now let's do, if you have this MBJ and then you say write MBJ, if there are 100 writes,
ट्रैफिक बढ़ जाएगा.
so there will be more write traffic. So you can also solve the consistency cache coherence problem by using a write through policy. In the write through policy, and it actually, if there are even multiple cores, even if there are 16 cores, it will never look into the private cache of other cores. It will never look into the private cache of other cores. Where it will get the data?
The last level.
The last level of the shared data. And the data will be updated in the shared data. And when the data will be updated in the shared data. So one thing, we can have for this shared data, we can also have a coherence directory. One option is to have a coherence directory that is shared among all cores, and other solution is to use a which policy?
Right.
Right through policy. Any questions?